Hello everyone, I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about energy band diagram in semiconductor devices. So in the previous lectures we have discussed about direct and indirect gaps, a PN junction and the voltage current characteristics of a PN junction. If you have missed out on those lectures, you can refer to the previous videos and catch up with the topics. Today's topic, as I told you, is energy band diagram. Let us see how we are going to discuss about this energy band diagram. First, we'll try to understand what an energy band diagram is. Then, we will see in detail about P-type semiconductor, the energy band diagram in a P-type semiconductor, then energy band diagram in N-type semiconductor, and then we will see the energy band diagram of a PN junction diode. And if time permits, we will also discuss about the biasing and different types of biasing. Now, let us see the definition for energy band diagram. So, it is a diagram plotting various key electron energy levels. Electron energy levels, when we say here, they are the Fermi levels and the nearby energy band edges, and they are plotted as a function of some spatial dimension which is often denoted by X. And why we are drawing these diagrams and how do they help us is, they help us to explain the operation of many kinds of semiconductor devices and to visualize how bands change with position. So for example, I'll draw a simple energy band diagram. So if you are taking energy along the y-axis and the spatial position along the x-axis, I will denote all the levels, energy levels that are occupied by the valence electrons. They are shown by valence band. So, the valence band denotes the energy levels of all the valence electrons. So, we are calling it as valence band. Now, I draw another band which is a conduction band. So, conduction band denotes the energy levels of all the conduction electrons. Conduction electrons here mean they are free electrons. So, when will the valence electrons become free? When we supply some external energy, and if the valence electrons can come out of the valence shell, they become free. And we call them as conduction electrons because they take part in conduction. And these energies of all the conduction electrons put together are denoted by conduction band. Now, I will denote the energy levels. I say this is EV. EV is the highest level in the valence band, topmost level in the valence band we are denoting by EV. And this is EC. EC is the lowest level in the conduction band. Means between EC and EV there is a gap which we call it as energy gap. So what the energy gap denotes here is the minimum energy that is required by the electron to go from valence band to conduction band. What do we understand by an electron going from a valence band to conduction band? Means it is the minimum energy required to make a valence electron free. So this is how we are denoting an energy band diagram. We are showing the electron energy levels and we are plotting the diagram for E versus X, I can say. So now, first we will see how the energy band diagram is for an intrinsic semiconductor. So what is an intrinsic semiconductor? It is a pure semiconductor. Intrinsic always denotes pure semiconductor. Pure semiconductor means all the atoms in the crystal belong to the same element. If I am taking a silicon crystal, all atoms in the crystal are silicon atoms, and if I am taking the example of silicon, it belongs to the fourth group, so it has 4 valence electrons. So each atom is surrounded by 4 identical atoms, and each atom possesses 4 valence electrons. Why 4 valence electrons? Because if you see the electronic configuration of silicon, you will see that all fourth group elements have 4 valence electrons. That is how they are placed in the periodic table. Now these 4 valence electrons, they form bonds with the neighboring atoms. With the 4 neighboring atoms, they form covalent bonds. And at 0 Kelvin, means at 0 Kelvin temperature, there are no electrons which are free. Means no electrons that are free means the conduction band is completely empty. So there is no conduction, and hence the electrical conductivity of the semiconductor is 0, means it does not conduct. So a pure semiconductor at absolute 0 will behave like an insulator. If you see the diagrammatical representation of what we have discussed, silicon, it has a 4 valence electrons. So each silicon atom is having 4 valence electrons, and these electrons are shared with the neighboring atoms. So these are the neighboring atoms. So this silicon is sharing 1 electron with this second, third and 4 neighboring atoms. The same way all the other silicon atoms are also sharing the electrons with the neighboring atoms. Here we have shown only 9 atoms, but there are n number of atoms if you are considering a silicon crystal. So at T is equal to 0 Kelvin, what we are observing is all the electrons, valence electrons are forming bonds, covalent bonds with the neighboring atoms, and none of the electrons are free. No electrons are free, means no conduction electrons. Now, if I have to represent the same thing on the energy band diagram, this is the energy band diagram. Energy band diagram for an intrinsic semiconductor, that is a pure semiconductor. We have taken silicon here. So, if you see the valence band is full, there are electrons in all the levels in the valence band. But if you see the conduction band is vacant, means there are no electrons in the conduction band. And now we are also showing this gap, e.g. if the valence electrons have to go to the conduction band, we have to supply a minimum amount of energy equal to Eg. Now, if you increase the temperature, as temperature increases, means if T is greater than 0 Kelvin, that means even at room temperature, some of the covalent bonds break. When bonds are breaking means the electrons become free. So these free electrons start conducting. So they become conducting electrons. So when they are becoming conducting electrons, they move to the conduction band. So when electrons from the valence band move to the conduction band, they leave behind holes in the valence band. So correspondingly, we have holes in the valence band. And what we observe here is the number of electrons in the conduction band is always equal to the number of holes in the valence band. So suppose if 4 electrons have moved from the valence band to the conduction band, so there will be 4 holes in the valence band. So this is the diagrammatical representation. So at a temperature T greater than 0 Kelvin, suppose we have considered some of the bonds, this bond is broken. So when the bond is broken, what is happening? This electron has become free. This is a free electron now. So when this electron has become free, it has moved out, there will be a hole here. A hole is nothing but a deficiency of electron, which we call it as vacancy. So what is a hole? A hole is nothing but a deficient site of electron. Where there is a deficiency of electron, we call them as vacant sites also. So a vacancy is called a hole and this is an electron. So depending upon the number of bonds that are broken, we have electron hole pairs that are generated. Why I am calling them as electron hole pair is when one bond is broken, one electron becomes free. Correspondingly, there is one hole in the valence band. So if in the diagrammatical representation, if we see previously at T is equal to 0 Kelvin, the valence band is full and the conduction band is empty. But now, when the bonds are broken, some of these electrons from the valence band, they have moved to the conduction band. You see, this is moving here, this has moved here. So there is movement of electrons. So this has moved here. So suppose here we have shown 6 electrons moving from valence band to conduction band. So there are 6 holes that are formed in the valence band. So this is what we call it as thermal energy breaking of covalent bonds. Why we are calling them as thermal energy breaking? Only when we supply energy. Here we have increased the temperature. So we are calling it as thermal energy. The bonds are broken. And because of the bonds that are broken, we have free electrons. And because of the free electrons, we also have holes and we are calling it as electron hole pair generation. Now, if you see the grammatical representation of this valence band and conduction band, and this is the Fermi level. EV, I told you, is the topmost level in the valence band, and EC is the lowest level in the conduction band, and EG is the gap between the valence band and conduction band, and this gap denotes what is the minimum energy that has to be supplied to the valence electrons to move to the conduction band. And then we also have another level we are showing as EF. EF denotes the Fermi level, Fermi energy level. EF denotes the Fermi energy level, or we may simply call it as Fermi level. Okay, so Fermi level denotes the highest occupied energy level, means all the energy states below EF are filled and above EF everything is empty. So that is what we see here as EF. So at T is equal to 0 Kelvin, the Fermi level lies exactly in between or in the energy gap, at the center of the energy gap. If this is the energy gap, it is exactly in the middle. And as the temperature increases, the electrons start moving to the conduction band. So the Fermi level starts shifting towards the EC. So this is how we see the shift. So at T is equal to 0 Kelvin, it is at the middle of the energy gap. And as the temperature increases, 300 Kelvin here is nearly the room temperature. So when the temperature increases, what is happening? As the electrons move to the conduction band, this Fermi level shifts towards the conduction band. Now we will see the energy band in a N type semiconductor. How the energy band is in a N type semiconductor. For that we need to understand what an N type semiconductor is. So when I say N type semiconductor, it is an extrinsic semiconductor. Extrinsic means impure. Extrinsic means impure. When I say impure, means you take a pure crystal and add some impurity to it, then it becomes impure. Impurity means here an atom from a different element. So here, when a pentavalent impurity is added, pentavalent, penta represents 5 and valent means valency electrons. So pentavalent impurity here means an impurity which has 5 valence electrons. So when it is added to a pure semiconductor like silicon, what happens then is 4 of the valence electrons of silicon form covalent bonds with 4 electrons of the pentavalent impurity. So they are forming covalent bonds with the neighboring atoms of 4 silicon atoms. And the 5th electron of each impurity is loosely held to its parent atom. And it can be easily detached by supplying a very little amount of energy. Means we try to understand here with the help of the diagram. So if you are talking about silicon, silicon has 4 valence electrons, and then arsenic, when we are adding, which is a pentavalent impurity, it has 5 valence electrons, 1, 2, 3, 4 and 5. So these are forming bonds with the neighboring atoms like this. So even after the bond formation, 1 electron is free. So for every atom that we are adding, there are free electrons that are generated, and we are calling them as free electrons or conducting electrons, and they can be easily detached by supplying very little amount of energy. So the energy levels are introduced to all the 5th electrons of the impurity atoms just below the conduction band. So what we have to see here is, when we are talking about the impurity atom N semiconductor, 5th electron, so it forms an energy level just below the conduction band, and we call them as donor levels. This is the valence band. This is the conduction band. This is denoted by EV, and this is denoted by EC. Now, all the electrons of the valence band are in this band, and their energy levels are denoted by valence band. Now all the conduction electrons which are free, the 5th, will be denoted here. Now after the covalent bond formation, the 5th electron, which is always free, it will form an energy level just below the conduction band, and we name it as ED, which is called the donor level. ED is what? It is donor level. They are called donor levels because they are always ready to donate 1 electron. And at room temperatures or very near to the room temperature, these electrons in the donor levels jump to the conduction band. Means with a very small increase in energy or temperature, the electrons that are present in the donor level can easily go to the conduction band and leaving behind few holes in the valence band. So what happens now here? Electrons are the majority carriers and holes are the minority carriers. And as there are excess conducting electrons, the semiconductor thus formed by doping pentavalent impurities, we call it as N-type semiconductor. So this is what we have discussed now. Silicon and phosphorus or arsenic, both are 5th group elements. So they have 5 valence electrons. So each electron which is free for each impurity atom that is added, they form an energy level, or I can say the energies of these free electrons are denoted by this level, which we call it as donor level. So at 0 Kelvin, they are in the donor level, but as the temperature increases, what happens? The electrons in the donor level, they will move to the conduction band. They move to the conduction band. So when they are moving to the conduction band, there are electrons in the conduction band and we will find holes here, and there are no holes in the valence band. So the Fermi level slightly shifts upwards towards the conduction band. So what happens now is the Fermi level will shift till here, because when you have electrons here, I say this is the highest level that is occupied. No? So the Fermi level definitely shifts towards the conduction band. And if you are increasing the temperature further, the whole concentration also increases. Means more and more bonds are broken and more electrons from the valence band move to the conduction band, and then there will be holes formed in the valence band, and ultimately the number of electrons in the conduction band will be equal to the number of holes in the valence band. So now coming to the p-type semiconductor, when trivalent impurity atom is added, trivalent here means, tri means 3. Trivalent means an impurity which has 3 valence electrons. An impurity which has 3 valence electrons, we call it as trivalent impurity. So we will be adding a trivalent impurity to a pure silicon, that is a pure semiconductor. Then what happens? Each impurity atom will form 3 covalent bonds with 3 of its neighboring atoms, because they have only 3 valence electrons. I am talking about the trivalent impurity which has 3 valence electrons. It will form bonds with the neighboring atoms, and always there is a deficiency of electron. Deficiency of electron to form the 4th bond. And if you need a closed shelf configuration or a octet configuration we call, or stable configuration, it needs 8 electrons. So from silicon there are 4, and from the impurity that we are adding, gallium, indium, whatever trivalent impurity we take, it has 3 electrons. So these 3 are forming bonds with 3 electrons of silicon, and 1 electron is always vacant. So what we say here is energy levels are created to the electron deficiencies. So just above the top of the valence band, and this level is just above the valence band, and we call them as acceptor levels. Why we are calling them as acceptor levels? Because they are always ready to accept an electron, because for stable configuration there is a deficiency of electron. So we are calling them as acceptor levels. Now let us see the figure here. We are talking about boron, which is a trivalent impurity. Trivalent impurity, it has only 3 valence electrons, and there is always a deficiency of electron. And this deficiency of electron we will call it as hole. And the silicon is having 4, so boron will form bonds with 3 of its neighboring atom, and 1 is always a vacant site, which we call it as hole. Now if this has to be represented in the energy band diagram, so this is the valence band. These are the energies of all the valence electrons. The conduction band is empty because there are no free electrons or conducting electrons. But now, because of the addition of a trivalent impurity, there is one level that is formed just above the valence band, which we call it as acceptor level. EA here is called the acceptor level. EA is acceptor level, which is ready to accept the electron. So these are the vacant sites. So at T is equal to 0 Kelvin, what we see is the valence band is full, but there is an energy level that is just above the valence band, which is having vacant sites and which is ready to accept the electrons. So when the temperature increases, the electrons in the valence band will move into the acceptor level, leaving behind holes in the valence band. So when the temperature increases, these holes that are filled by the electrons from the valence band. With a slight increase in energy, the electrons from the valence band move to the EA level. That is, they will fill the holes in the acceptor level. And then because of that, what happens? The Fermi levels shifts downward and it is slightly above the valence band. So whenever we are having this, we'll have the Fermi level shifting towards the valence band. So this will be the position of the Fermi level. And as the temperature increases, more and more bonds are broken and then the electrons will move into the conduction band. Then what we see here is the Fermi level also starts shifting as more and more electrons move to the conduction band. The electrons, with the movement of electrons, the Fermi level also shifts to the intrinsic level. So let us compare how this Fermi level is in intrinsic, N type and P type. So intrinsic is a pure semiconductor. What we have seen in a pure semiconductor, this is the valence band, this is the conduction band, and the Fermi level lies exactly in between the energy gap. This is the energy gap Eg. The Fermi level lies exactly in the middle of the energy gap. Now when it comes to N type, when we are adding a pentavalent impurity, there is a donor level that is formed, Ed. Ed is the donor level and the Fermi level lies very close to the conduction band. This is very important for us to understand the energy band diagram of a PN junction. So when we are talking about a PN junction, how the energy levels are in P type, how the energy levels are in N type. If you are clear about it, then it is very easy to understand the energy band diagram when a PN junction is formed, when we are combining or when we are forming a P and N junction. So this is how the Fermi level lies in the middle or below the conduction band and above the donor level, in between the two. Coming to P type, where we are adding a trivalent impurity, there is always a deficiency of electron and we call it as hole. There is an acceptor level that is formed above the valence band. This is the acceptor level above the valence band. Therefore, the Fermi level shifts towards the valence band. So the Fermi level is very close to the valence band. As we move forward to discuss about the PN junction, these two things we have to remember. In N type, the Fermi level lies very close to the conduction band, and in P type, the Fermi level lies very close to the valence band. Now coming to the energy band diagram. So when we are joining the valence and the conduction bands in N type material are at a slightly lower energy level than in the P type. So now I will denote this. If you see here, this is the demarcation for the PN junction. This is the junction. On this side, we have the P region. So on the P region, this is the valence band. And this is the conduction band for the P region. We are talking about PN junction now. So we have taken a P type material and we have taken an N type material. We have seen different methods also how a PN junction is formed. So we will use one of the methods to form a PN junction, and we are representing the energy levels with the help of the energy band diagram. And now this is how the energy levels are in P type, and in N type, this is the valence band and this is the conduction band. So from the diagram, what we observe is the energy levels in the N region are at a slightly lower level than the P region. I think this is evident from the figure that they are at a slightly lower level. This is the valence band lowest level and this is the valence band lowest level in N region. So it is slightly less. Why it is like that? Because P-type material has trivalent impurities and N-type material has pentavalent impurities. trivalent impurities exert lower forces on the outer shell electrons than the pentavalent impurities. So in case of a trivalent impurity, there are lesser forces on the valence electrons. So lower forces mean that the electron orbits are slightly larger and hence they have greater energy. So this is the reason for the P side having higher energy levels when compared to the N region. So N is always at a lower level compared to P because there are lesser forces that are exerted on the valence electrons. They have more energy, larger orbits, and therefore more energy. I think this is very clear here. You can see it very clearly. So P region, N region, this is the PN junction. This is the valence band. This is in the P region. This is the valence band. In the N region, you can see the energy difference. N is always at a lower level when compared to P. And the same thing happens with the conduction band also. This is the conduction band in P type and this is the conduction band in N type. Again, this is at a lower level. Now, when we see P type, in P type, you see holes are the majority carriers. These are holes. Holes in the valence band. They are majority carriers. And these are electrons which are in the conduction band. They are minority carriers. This is also one more point you need to remember to understand the energy band diagram and the movement of electrons and holes from across the junction. When it comes to N type, what we see here, electrons are the majority carriers and holes are the minority. Minority carriers are holes on the N side. Majority carriers are electrons. One important point to remember. So when it comes to the P side, minority carriers are electrons and the majority carriers are holes. So the valence and the conduction bands in the N region are at a lower level than those in the P region, but there is a significant amount of overlapping. This is very significant and plays a very important role. What you need to understand is, here if you see this region and this region, there is an overlap. There is an overlap of the energy levels of P and N region. So because of this overlap, what happens is the free electrons in the N region that occupy the upper part of the conduction band, that is in terms of their energy, can easily diffuse across the junction. So if I say here, this is the overlap that is there between the P junction and the N junction. And these are the electrons which are lying in the top levels of the conduction band. And these can easily slide over into the P type. They do not require any energy, additional energy. We need not supply any external energy. But because of this overlap of energy levels, the electrons from the N side can easily diffuse. Diffuse here means what? We have already discussed this term diffuse. Diffusion is a process of movement of charge carriers always from higher concentration to lower concentration. And you see here the majority carriers are electrons. Electrons are in majority here, but here they are in minority. Electrons are minority. So these electrons can easily diffuse from N type to the P side. And they temporarily become free electrons in the lower part of the P region conduction band. So when they come here, they settle down in the lower part of the conduction band. But after crossing the junction, what happens? These electrons quickly lose their energy. When these electrons which are moving from N side to the P side because of the overlap, they lose their energy. When they lose their energy, what happens? They fall into the valence band. So after losing energy, they fall into the P region of the valence band. And as this process of diffusion continues, what happens here? The depletion layer begins to form. What is a depletion layer here? A region that is depleted of charges. So I can say here, most of the electrons that are there in the overlap region have moved to the P region. Now if you see here in this diagram, once the diffusion is complete, there is no more overlap. If you see here the diagram, you can clearly understand. So the electrons from the N side have diffused into the P type and they lose the energy, they fall into the P type. And what happens here is there is a region that is formed which we call it as depletion region. Means the electrons that have shifted from here to here, they leave behind positive ion sites. They are positive ion sites. And here there are negative ion sites. So there is an electric field that is developed which will sweep away all the charges. And this region is free of charges or depleted of charges. So we call it as depletion region. So the decrease in the energy level of the conduction band in the N region is due to the loss of higher energy level electrons that have diffused across the junction to the P region. Now we are seeing here there is a lowering of energy level in the conduction band. This happens because of the diffusion of electrons from N side to P side. All the higher energy electrons on the N side have diffused onto the P side. That is why the energy level is lowered. Now there are no electrons that are left in the N region with enough energy to get into the P region. So here, if I see this alignment, there are no more electrons that can go from here to here. There are no electrons here. So no electrons with that energy which can diffuse into the conduction band. So what happens here is the conduction band is lowered, and in the same way the valence band also gets lowered. So what we need to understand is the gap remains the same. So the energy level in the N region has shifted downwards. The same way the energy level of the valence band also has shifted downwards. If you see here, this is the valence band and this is the valence band. So this also has shifted. So the energy gap between the valence band and the conduction band always remains the same. So at this point, the junction is at equilibrium and the depletion region is complete and the diffusion has ceased. So three things we are observing here. What is the first one? The junction is at equilibrium and the depletion region is complete and the diffusion has ceased. They are interconnected. Diffusion means the process of movement of electrons from higher concentration to lower concentration has ceased. Why it is ceased? Because there are no more electrons with that energy to go in the, but due to overlap. And second thing is because of this movement, there is a depletion region that is formed and there is no further movement of electrons and it is in equilibrium. So there is an energy gradient across the depletion region and that will act as an energy hill. What we are trying to understand now is because the level has lowered, if the electrons from the N region have to go to the P side, they have to climb this hill. This is the hill that we are calling here. So the electrons from the P N side has to climb this energy level, or I can say have to overcome this barrier and then only they can move on to the P side. So what about the contact potential? The contact potential VB across the junction is due to the potentials of the depleted region on the N side denoted by Vn. So Vn denotes the potential on the N side and Vp denotes the potential on the P side. If we are talking about this is the N side and this is the P side. So this is the depleted region. So if this is Vn, this will be Vp, and the barrier potential Vb is given by Vn minus Vp. So this denotes the contact potential or the barrier potential Vb, which is Vn minus Vp. Now this contact potential, it separates the energy bands in the p-type and n-type crystals, since there is no current flow at equilibrium. So when the junction is at equilibrium, means there is no movement of electrons and holes. So the electrons cannot move from n side to the p side, but it should have a common Fermi level. We have already discussed about the Fermi level. Now let us see how the Fermi level is in p type. So this is the p region. So this is the valence band and this is the conduction band. ECP denotes the lowest level in the conduction band in p region. So we are calling it as ECP. And same way EVP denotes the highest level in the valence band in p region. And this is the Fermi level. This is the Fermi level. As discussed, in p region, the Fermi level is shifting towards the valence band. So this is the Fermi level. Now when it comes to n region, this is the n region. In n region, what we have here is ECN, lowest level in the conduction band in n region, and this is EVN, topmost level of the valence band in the n region. And in n side, the Fermi level lies very close to the conduction band. This is the Fermi level. But if you see, when it is joined at the junction, if you see, the Fermi level is common. If you see separately, the Fermi level lies very close to the valence band in p region, and it lies very close to the conduction band in n region. So, a PN junction diode, the valence band and the conduction band energy levels EVP and ECP of the p type are at a higher level compared to the valence band and conduction band EVN and ECN. We can clearly observe if this is ECP, this is ECN. So ECP is at a higher level than ECN. This is EVP, that is the valence band topmost level in p region, and this is EVN. So EVP is at a higher level than EVN. So the electric field across the junction is given by EB, which is EVP minus EVN or ECP minus ECN. Both mean the same. Whatever the gap here is, it is the same here also, which we call it as energy gap and denoted by EVB. So if you see the picture as a whole, when there is no voltage that is applied, if you see here, this is the p type and this is the n type. There is always an uphill for the electrons on the n side to move on to the p side. So unless they move up the hill, they cannot go on to the p side. Means there is a barrier that is formed. So when there is no voltage at equilibrium, the electrons from the n side cannot move on to the p side. But when a voltage is applied, the barrier potential is reduced and there will be movement of electrons from n side on to the p side. And when these electrons move from n side to the p side, there always occurs whole electron recombination. What we have seen is these electrons which are moved on to the p side will quickly lose the energy and they jump into the valence band. So when they jump from higher energy level to lower energy level, they will always release the energy. So there will be whole electron recombination. That is what we are going to see in the next topic. So let us stop here and see you again in the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.